we're going to look at inverse functions. So in the last video, we looked at functions map an x to one unique y. And if it's a one-to-one function, then that y can map back to one unique x. And how do I map backwards from y to x is by using an inverse function. So an inverse function undoes whatever the function did. So if we think back to our function machines, if I have a function here let's call it f of x, and I plug in some input x, then my output is going to be f of x. Well, if I take that f of x and then I plug it into a new machine, if that new machine is actually the inverse function, which is notated like that with a -1 superscript, then if I get that x back, that second machine is undoing whatever that first machine did. So for example, maybe f of x is to add 5. Then f inverse of x would be to subtract 5. It just undoes whatever that first machine did. So if I compose those two functions like this, then I get x back. To make sure that it's an inverse, I have to be able to switch the order of those machines, because if one function is an inverse of another, then they're inverses of each other. So I'm actually going to go ahead and rename this f inverse as just another function called g. Keeps it a little cleaner. So now I'm going to put the g function first. So if I put x into my g machine, then out comes g of x. And if I take whatever came out of that second machine and put it into the first machine and put it into another machine of f, and I get an output of x, if I get both orders of those machines on my input, after going through both machines, I end up getting my input back as my output. That means that these two machines, or these two functions, are inverses of each other. They're undoing. The second machine undoes whatever the first machine did. Okay, so that's our definition of inverse right here. If f and g denote two one-to-one functions, so they have to be one-to-one, because remember our in the top right corner here, our function goes from x to one unique y, and y goes to one unique x. We have to have that situation before we can make sure we get that one unique x back out of the second machine. So it has to be a one-to-one function. And then the functions undo each other. So whatever I put into both machines is what I get out. Then these are inverses of each other, and we denote it, that f with the superscript and -1. Notice that is not an exponent. So exponent, like if I had x to the -1, an exponent would tell me that this is equal to that. But that's not what's happening here. That -1 is really strictly a notation that means f inverse, or the inverse function of f. So please note that f inverse is not equal to the multiplicative inverse, or the 1 over f, or an exponent. All right, so let's see what these functions look like in practice. So I'm going to do one example here where we're going to verify the function given here is the inverse function of this guy, f of x. So to verify they're inverses of each other, I'm going to compose both functions in both orders and make sure I get my input back. All right, so my purple function, the f inverse, I'm going to call it g because I think it looks cleaner on my paper. I get a little less confused when I do g of f of x. So I'm inputting f of x into g. I'm going to input that, and I want to try to get x as my output. If I get x, I put in x and I get x as an output. That's halfway there to proving that's inverse. I also have to prove, though, that it works if I switch the orders of the machine and I put g into my f of x. So g is my input and of the f of x function. So let's reverse these. Let's evaluate these. So I'm going to start with my g of f of x. So remember to compose functions. I can rewrite the function using a placeholder or parentheses for the x. So I go x minus 1, that whole thing cubed, plus 2. That's g of x. Only my input is going to be f of x. So that's what goes in for x. That's all this. So that's cubed root of x minus 2 plus 1. So now I need to simplify that. And I get inside of that bracket of the cubed bracket, I can switch the order of the parentheses around the addition to be 1 minus 1. I can switch that order because addition is associative, so I can change who I associate with first. And then when I do that, my 1 minus 1 cancels, and I'm left with the cubed root of x minus 2 cubed plus 2. And the cubed root of x minus 2 cubed is x minus 2. Those two cubes cancel. The cubed root and the cube cancel. And that gives me x minus 2 plus 2. And again, I can change the order of those parentheses because addition is associative, so I can change that to minus 2 I'm going to say a plus a negative. I'll write that as plus a negative 2 plus 2. And then those 2's cancel, and I get x as my output. So halfway there, I have to prove it works both ways. So now I'm going to input g of x into f of x. So I'm going to write my f of x function with a placeholder for the x. So that's cubed root of x minus 2 plus 1. And I'm just going to write this a little bigger with a little bigger of a placeholder since I want to fit that whole function in there neatly. So I'm going to write cubed root of x minus 2 plus 1. And the thing that goes inside that placeholder is the g of x. I'm inputting that for this x here. So that's all of this. So that's an x minus 1 cubed plus 2. So the first thing I do is change the order of the association. I can change the association of the parentheses inside that parenthesis. So I get that equals the cubed root of x minus 1 cubed plus 2 minus 2. So just switching those parentheses around the addition, so I can do that because addition is associative, so I can change who I associate with first. And simplifying under the radical, the 2 minus 2 cancels. And that leaves me with cubed root of x minus 1 cubed plus 1. And the cubed root of a cube is what's underneath, so that cancels, and I get cubed, oh, no, the cube's gone. X minus 1 plus 1. And I can change the order of that parenthesis again because addition is associative, so I can go x plus a negative 1 plus 1. Those cancel, and I'm left with just x. So now I've shown that both machines undo each other, which means that G and F are inverses of each other. Okay, and then the second part of this question is asking me to, let's see, graph both f and its inverse on the same axis to show that it's symmetric about that line y equals x. When two functions are inverses of each other, they'll be symmetric over y equals x. The y equals x line is this line right here. I guess I'll just draw a light green line there. So that's the y equals x line. So if they are inverses of each other, they should be symmetric over that line, like that line's a mirror between them. So let's see, let's draw f of, or g, I should say, or the f inverse in purple. So that is the x cubed graph, which looks something like this. Let me try that again. I'm going to try to do it in one swoop so I can... There we go. That came out good. So that's my x cubed graph, and it is, using my transformation rules, it is shifted right 1 unit and up 2 units. So it's right about like that. So there's my g of x, or the f inverse. And my other graph is a cubed root function. So that one, let's use an xy table because we don't have as much experience with that graph other than knowing it's the inverse of x cubed. So let's plot a couple points there. So a good point from that purple graph was the 1, 2. So let's see if we switch the 2 and the 1. So let's input 2, and then I get 0 plus 1, so I get 1. So that point goes to 2 1s. So see how that's flipping over that green line. Let's pick another point from this graph. Let's see, there's one here over at 0 1. Let's see. So let's input a 1 and see if we get a 0. So if I input 1 there, I get negative 1 minus 2. So that's cubed root of negative 1, which is negative 1 plus 1, which gives me 0. So that point reflects to here. Let's do another one. Let's do brown. So let's check this point. Let's see. So that is 2, 3. So I should be able to find a 3, 2 on the other graph. So if I plug in 3, I get a 1 under the cubed root. So the cubed root of 1 is 1 plus 1, which gives me 2. So 3, 2. So it's, again, reflecting over that green graph. So everything reflects over that green graph, green line. Let's see if I can do this. So that kind of goes in and then like that, kind of. That's not great, but that's better. All right, so those two graphs, that brown one is, oh, I should have done that on blue. Let's see if I can just change that to blue, since my F was supposed to be blue. There we go. So now I got my F in blue, my G, or my F inverse, in purple, and the green line is a line of symmetry. And that is how we do 25 through 34. And that is inverse, our little intro to inverse functions.